So good morning, good afternoon, or good evening, wherever you are. Welcome you to the Matrix online seminar. And today we're very fortunate to have Professor Peter Buhlmann from ETH Zurich online. It's early in the morning for him, but very glad that he's been able to join us. Peter studied at ETH Zurich and graduated in 1993, did a few years postdoc in Berkeley and returned as a lecturer in 1997 to ETH, where he's been ever since. He's has made significant contributions, very well-known name in statistics and machine learning. And he was a speaker at the International Congress of Mathematicians in Rio in 2018, and is a fellow of both the Institute of Mathematical Statistics and the American Statistical Association. So welcome, Peter. I'm looking forward to your talk. I'd like to thank the partners and sponsors of Matrix before we start, the Australian National University, Monash University, and the University of Melbourne, as well as the ASC Centre of Excellence, ACEMS. All right, over to you, Peter.
Okay. Okay, well, thank you very much for this nice introduction. It's great to be here, at least online. It's a great opportunity to be just around the globe with all of you. So here's the title of my presentation: Invariance, Causality, and Robustness in Statistical Learning. I first would like to acknowledge maybe my main collaborators in this research. This is Dominik Rotenhäusler, Niklas Pfister, Jonas Peters, and Nikolai Meinshausen, my colleague at ETH Zurich. So my title has Statistical Learning in it. This great book by Hastie, Tibshirani, and Friedman, published 20 years ago. These people have built a wonderful bridge between what I would call statistics and machine learning. It's really a great resource, but there is nothing in the book, and actually quite little in the machine learning community until recently, about causality, which is perhaps a very dangerous word, and also what I want to focus on, and that's the second part of my title, invariance, stability, and distributional robustness. So let me start a bit with some sort of an overview. Nowadays, as we all know, we have multiple of terabytes of data, we have huge amount of data, and we want to extract something useful. We want not just black boxes, we want to gain understanding, we want to get new insight. And some people call this maybe interpretable AI in modern language, or interpretable machine learning. And I'd like to call it also interpretable statistical inference in modern context. So as we will argue in this talk, as I try to convince you, is that better understanding, having more insight, actually exhibits also increased robustness. While this is maybe no surprise in vague scientific folklore terms, many people would agree that if we understand things better, these systems are maybe more robust, but that needs to be a bit mathematized, and this is what I want to explain a bit today. I would also like to come to the opposite pole, maybe here, of blind machine learning, and just briefly remind you about the replicability crisis in science. I guess many of you have heard about it. If you read in Wikipedia, it says that scholars have found that the results of many scientific studies are difficult or actually impossible to replicate. And so here is a famous pioneer who made us aware of this replicability crisis. This is a picture of John Ioannidis. He's professor at the School of Medicine in Stanford. He has a courtesy appointment with statistics. And he published in 2005 this kind of quite famous paper, Why Most Published Research Findings Are False. I mean, hopefully this is not a false result. He argues that it is extremely difficult to replicate studies. So if you have some finding of a study, it's extremely hard to see replication in another study. So kind of obviously assigning some sort of statistical uncertainties, maybe stability, robustness, are potentially useful to at least partially improve the situation a bit. And I try to come back to this problem towards the end of the talk again. So what we're interested in is really to have methods, algorithms, tools, which are better in terms of replicability, stability, increased robustness, and better interpretation. So let me start maybe how the classical statistical framework goes on that. I have here the title of the slide, Single Data Generating Distribution and Corresponding Statistical Inference. So here are pictures of Mosteller and Tukey, and they wrote in 1968, one hallmark of the statistically conscious investigator is his firm belief that however the survey, experiment, or observational program actually turned out, it could have turned out somewhat differently. So in statistics, we kind of adopt a certain framework to address this issue, and we kind of say it's very standard now in every textbook that the data which we observe, these are values, numbers, right? They're fixed, they're kind of small, Z1, Z2, Zn, but they're interpreted as outcomes of random variables cap Z1, cap Z2, cap Zn. Typically, we make maybe an IID assumption, independent, identically distributed, or a bit more generally, for example, we say they're realizations from a stationary distribution, a probability distribution P0, which generates the data. So I have this data generating P0. This can be from a possibly very complex infinite dimensional model, nonlinear regression classification, could be from PDs and so on and so forth. And of course, there's a huge amount of history to do or address this goal, namely inference from data about a functional of this data generating distribution P0. So I start here with pictures from Grant and Petty, 1662. They, I think, produced the first life table. Then I have a couple of other famous names, Bayes, Laplace, Gauss, and so on and so forth. And most of this is about generalization to a population from the same distribution P0 as the one which generated my data. So we say, okay, the data which we have should be representative for the conclusions we make for the population of interest. That's kind of the standard statistical framework. So today I want to say something about how can we generalize to potentially new data generating distributions. So classical framework, I mean, I'm kind of exaggerating here a bit, but a very classical framework cannot do that, cannot really generalize well beyond the data generating distribution P0. So what we want to do here, this is my setting, is I say I have observed data from a distribution P0, and I want to say something about a new P prime, which is different from P0. Okay. That's maybe not the most realistic setting which we have nowadays. This is a bit of generalization, what I will look at. I say, okay, I have a lot of data. It might come from heterogeneous populations, from subpopulations over different environments, different scenarios, and every subpopulation has a data generating distribution. Let's call it or denote it by PE, and this little e here denotes a certain environment, a certain subpopulation, and so on and so forth. And this little e here is in the space script D, and during my talk, script D is the space of observed subpopulations, observed different scenarios, and so on and so forth. And again, I want to say something about a new PE prime, where E prime is not among the observed subpopulations. So obviously some kind of extrapolation is needed here. I tried to convince you that some kind of causal thinking can be quite useful in this context. People also refer to this problem as the transfer learning problem, domain adaptation. These are subfields in machine learning. Okay, so here is a cartoon illustration what I mean. This is a self-driving car, it's an autonomous system. This is not what I'm working on, but kind of explains quite well what I'm aiming for. So this autonomous system is trained on many design scenarios, different experimental conditions, from this space script D. This is observed, this is designed, but of course you want to say something about a new scenario E prime, which has never been observed before in the training phase. Okay. So this is more the area I'm working in. I have quite a bit of exposure to life science applications, and here is a small glimpse on a big project. So this is a GTEC consortium project. GTEC stands for Genotype Tissue Expression. This is gene expressions in human tissues, and a very small aspect of this big GTEC data is as follows. It's just an example of what I mean with my framework. There are 13 different tissues. These are human tissues, say from liver, skin, hair, and so on and so forth. I can encode these 13 different tissues as 13 different subpopulations, and these are the labels 1, 2, up to 13 in my space of observed subpopulations. These are my different situations. Within every tissue, we measure gene activities, quite a few of them, and we aim to say something about a new tissue E prime, which is not among the observed 13. This is very noisy in high-dimensional data, and I'll come back later to this problem again towards the end of the talk. I want to show you increased replicability in this kind of framework. Okay, so how can we try to go for this? How can we try to do this extrapolation from these subpopulations which we see to something which we've never seen before? So this is a kind of the oracle dream or oracle world, which is totally unrealistic, but which describes the setting. I'm thinking of a response, a target, or people call it also a phenotype variable Y of interest. There are explanatory variables, features, covariates. These are the x's, x1, x2, x3. You see here x1 influences Y directly, x2 as well, and x3 is influenced by Y. And there are quite a lot of non-observed hidden variables which are causing quite a bit of nuisance here. So if there is a hidden variable, this would be a hidden confounder. It's very hard to distinguish the effect from x1 to y in presence of such unmeasured hidden confounders. So this is the unrealistic oracle world. The entire system would be known, and if I would have this knowledge, then I could answer many questions. What you observe is only y and your explanatory variables x1, x2, x3. And now you can start to do standard statistics, right? You can do correlations among these variables. You can run regression among these variables. And if you do so, if this is actually your true system, then what happens is all these variables are dependent, are associated with each other. So we say way too many relations, many of them are spurious. And also we see no directionality. We cannot infer whether x1 kind of influences directly y or vice versa. So the goal somehow in my talk, in my research here is I ideally would like to infer the true relations and the directionality between these explanatory variables xj and y. I do not see the hidden variables, and because of that, this is an extremely ambitious task. It's very, very hard, very difficult, and it cannot be solved by standard regression or modern standard machine learning tools. They cannot cope with hidden confounding. They cannot cope with directionality. This is a very ambitious problem. I'll explain a bit about it today. Perhaps a bit more realistic is aim number 2. At least I may want to do some robust prediction of y from my explanatory variables. I just want to predict y from x. I don't know whether x is directly influencing y or not, but I can use it as a prediction tool. And I want to do this prediction such that it is robust over my various perturbations, my various subpopulations, my various environmental conditions. These two aims, 1 and 2, they're actually quite closely related, as I will explain in my talk. Okay, so how do we model this from a more mathematical point of view? So we have this graph, right? We have knowledge about the structure maybe here. And so once we have the structure, we specify function models for every random variable. This is called a structural equation model. So I collect all my variables, all my nodes in the graph. here into this vector W. This is the Y, x1 to xp, and I have hidden variables h1 to hq. And for every component, I say wj is a function. This is kind of an algebraic equal sign, is a function of the parental variables, comma, error term epsilon j. You can do this for every component. And an important assumption here is that these error terms, these innovation terms, they're jointly independent. Now, of particular interest is the Y equation. I'm mainly interested in getting know-how. How does Y depend maybe on the other variables? So this is my main equation of interest. Y is a direct function of the parental variables, which I observe the x's, and potentially unobserved parental hidden variables, comma, error term. So this system here creates or induces a probability distribution, a joint distribution among all these variables. Let's call it P. And this P is well known to be Markov with respect to the underlying graph. This could be the local or global Markov properties. This is known since a long time, and it's very nicely written up by, say, Stefan Lauritsen in his book. So here's a bit of side remark. Many people then said, okay, now we have data and we can try to learn the structure of the graph from the data. And that's actually impossible in general without additional assumptions. It's well known for the experts here also that one can only estimate equivalence class of graphs. The problem is not identifiable, and people call this the Markov equivalence class. They can be quite large, and you cannot distinguish between equivalent members. So this started about 30 years ago or even longer, and then there came algorithms where given data, they output a Markov equivalence class of graphs. That's not what I primarily want to talk today. I want to tell you that these structural equation models are actually very useful to use them as a model for perturbations, for new scenarios, for new subpopulations which you've never seen. So this is models for perturbations using these structural equation models. And I just show you a very simple didactical example, which is maybe unrealistic in practice, but it's very easy to explain. And this is the Pearl-Do intervention model. So suppose you have a system of interest. It has a certain graph. It has 3 explanatory variables, a Y variable. I can write down the corresponding structural equation model. So you start with the source node. This is just kind of a noise term. Then x2 is a direct function of x3, comma noise. x1 is a function of x2, comma noise. And y is my equation of interest. It's a function of x1, x2, comma noise. Okay, that would be what I explained before, my structural equation model. Now I do an intervention at the second variable, and I make a very particular intervention, a so-called do intervention, which means that you set the value of this random variable x2 to a certain specific value, again, the real number, little x. And the question is, what is the model for this do intervention? So you need to make a model here. And the model is as follows. In terms of the graph, if you intervene here at x2, you really make an outside intervention, and all incoming other relations are cut, right? It doesn't matter how x3 here influences x2, because you just set x2 to this value, little x. And then Pearl says in his model, well, and now you inherit all the equations also to this graph. And that means here I have my source node. Here I have x2 is set to little x, and now you propagate this intervention effect to the other variables. x1 is the same function, f1, you plug in little x, comma, epsilon 1, the same distribution for epsilon 1, and eventually y is the function of this kind of propagated intervened variable x1, x2, and epsilon y. The important point is you really dynamically propagate the effect of this intervention. If you intervene here, it propagates through the graph. This is a very simple-minded model. It's maybe not realistic in practice, but it's very beautiful to explain, and it's highly popular actually in the machine learning community. There are many other perturbation models based on structural equations. For example, we can have additive shifts and similar things, and all of them exhibit dynamic propagation of interventions. If you intervene somehow at a variable or a couple of variables, this effect dynamically propagates through the system. There is an ordering for this propagation. That's the ordering of the graph, of course, right? Here we know how it propagates. If we intervene at a variable, it's very plausible how this works. But given data only, the ordering is unknown. This makes it difficult, and this is much more complicated in that respect than, say, propagation along time, like, say, in differential equation models in dynamical systems, where you have time as an ordering. Here, the ordering is in principle unknown. I try to argue that in this difficult world, causal thinking is kind of useful if we want to generalize or transfer to new situations with unobserved data generating distributions. Why? Causality, in a nutshell, is giving us a prediction, a quantitative answer to a, I call it a what if I do, what if I perturb question. But the perturbation, the new situation is not observed. I put here two pictures. This is Judea Pearl's book on causality, a great resource, and here a picture of Judea Pearl, who was really also a pioneer in formalizing causality. So many modern applications are faced with such prediction tasks. Say in genomics, you could ask the question, what would be the effect of knocking down the activity of a gene on, say, the growth rate of the plant? What would be the effect if I knock down gene number 7 on the growth rate of the plant? The point is, I want to predict it without having any data on such a gene knockout on number 7. Okay, you want to predict this gene knockout. Advertising in e-commerce is the same thing from an abstract point of view. What would happen if you show a person XYZ an advertisement on social media and you have no data how person XYZ reacts on advertisements, or also no data from similar person than XYZ? Policy making, what would happen if you introduce a new health policy, and so on and so forth. So the term causality is perhaps a bit overly ambitious. It can be very philosophical, but here, in my view and my research, it's really about predicting intervention effects. What would happen if you perturb, if you assign, if you make a do intervention, and you have never seen that perturbation, that assignment before? I try to convince you a bit that heterogeneity in the data, and this is connected into robustness, and a bit of causality can be very useful to address these questions. I will use a so-called invariance and stability principle. I'll explain that. I will not go over trying to estimate Markov equivalence classes of graphs with certain algorithms. And let me start by putting up the setting again, which I introduced quickly before. So we assume that we have heterogeneous data actually from different known observed, say, environments or experimental conditions or perturbations or subpopulations. This is denoted by a little e. From this space, script E of observed subpopulations, observed different experimental conditions. I'm looking at a regression classification type problem. I have explanatory variables X, a response variable Y. They have a distribution P, and that always depends on the subpopulation you're looking at the experimental condition E. Examples, say you could have data from 10 different countries, and then of course this script D would be encoded with the labels 1, 2, up to 10. Each country could have its own distribution for X and Y. I also gave you as an example the data from the 13 different tissue types in this GTech data. So the script D again is 1, 2, up to 13 with the labels. Many large-scale data applications come from heterogeneous data, from different experimental conditions, different subpopulations. Okay, now we consider many possible but mostly non-observed environments or subpopulations or perturbations. And in my talk, they're coming from a space script F, which is much, much larger than the observed script D. Examples for this script F, this could be the 10 countries which I have in the data set from script D, and maybe all other countries in the world, all other subpopulations in the world. Or it could be the 13 different tissue types in my GTEC data. This is from script D, and many new tissue types which I've never seen before. And the problem here is, what I want to look at is very pragmatic. Predict y given x, that's a standard thing, such that the prediction works well, is robust, is replicable for these many possible new environments, from this much larger space script F, based on data from much fewer environments, what you have observed in your different subpopulations from script D. So here's again the cartoon illustration, right, with the self-driving autonomous system. So it's trained on designed known scenarios from my script D, but you want to have predictions which work well, which are robust for new scenarios from this script F, which the system has never seen before. It's a very important problem in reliable machine learning. So here's again my problem, predict y given x such that prediction works well, is robust, replicable for these many possible new environments from this much larger space script F. So if we mathematize this problem a bit, for example, with linear models, we can ask for the following. Let's look at the expected squared error loss, and I take the worst case expected squared error loss, the worst case risk over all possible future scenarios in this script F, and I try to find a regression parameter which optimizes this. So people would call this robustness, right? Because you really try to find a parameter which is good over a whole range of possible scenarios. And I also call it, this is closely related to causality because it deals with a problem with perturbations which you've never seen in the data and you want to do predictions. And so here is in a nutshell one of the big important results, which are not too hard to prove, but it's very important to shift maybe the focus a bit what causality could also mean. Many people think about causality getting the graphs right or kind of predicting interventions, which is quite close what I want to do here. But here I can really make a connection as follows. So if I look at linear models, in a nutshell, one of the results is as follows. I look at perturbations at future scenarios. I need to mathematize this a bit, formalize a bit. They're such that they do not act directly on y. So in terms of a graph, you could look at this as follows. You have x, you have y, you may have an internal system parameter. This is kind of the causal parameter. I just define it in a second. And we have perturbations, subpopulations from script E, right? They may act directly on X, but they do not act directly on Y. And then you try to solve this worst case risk optimization problem over all possible perturbations which act on X, but not directly on Y. And the solution of this worst case risk optimization problem is what people call the causal parameter. It is this internal system parameter. In a linear structural equation model, this is what I had on a previous slide. It is really the regression parameter in my structural equation model. So y is a function of the parental variables, and this function is linear and has certain regression coefficients, and that's this beta 0. So we call beta 0 the causal parameter. These are just all the components from the parental variables. Now, we can also look at hidden variables. We have a structural equation with hidden variables. I still look at the regression coefficients, which correspond to observed variables, and I call these the causal parameters. So this worst case optimization problem actually has the same solution, even if we have hidden confounding variables. If we want to optimize over all possible perturbations, all possible future scenarios which do not affect directly this y, which do not affect directly the hidden variables, then the solution to that is what people call the causal parameter. It's here, it's this internal systems parameter. Okay, so here is again the picture, and the point is this one here. The causal parameter optimizes worst case loss with respect to very many unseen future scenarios. This is an important point to keep in mind. This is actually known since quite a long time. And I put here a picture of Trygve Havelmo. He later got the Nobel Prize in economics, a famous person in economics. Already in his 1943 paper, implicitly Havelmo knew that causality and this kind of distributional robustness property, if you look at perturbations which do not act directly on y and h, they're intrinsically related. Today, I want to give you kind of a constructive method how you can actually exploit this. How can you exploit this relation between causality and this distributional robustness? Okay, and this is what I want to explain now a bit. We call this anchor regression. And this is a way to formalize this extrapolation from the space of observed environments, script D, to the space of future environments, future scenarios, script F. The environments from before, they have been denoted as little e. They are now modeled as outcomes of a random variable, and I call this an anchor A. You will see in a minute why I call this an anchor. So here is my anchor variable. Here is my system of interest. There is an internal systems parameter, a causal parameter. There is potential nuisance with hidden confounding. Now, if you assume that this anchor variable, these environments only influence the x, but not the h, not the y directly, this is well known. This is the instrumental variables regression model, a very popular model in economics, econometrics. There's a huge assumption here saying that this A, they call it an instrument, I call it maybe an environment, that this A only affects X. It does not directly affect Y, this is forbidden, and in particular does not directly affect H. And that's a huge assumption. How the heck can you know that, right? H is hidden. You cannot even name what it is. You make a huge assumption that this does not affect something which is hidden. So we relax this assumption. We say, okay, I have my environments, and we allow that it acts directly on Y. We allow that it also acts directly on H. The only assumption which we make here is that A is an anchor, a source node in the graph. People in economics would call it an exogenous term. This is the only assumption. You can also allow for feedback loops. That could be quite important. So these are multidimensional variables here and there. Now we have a structure, a graph. Now I put a quantitative model on the structure, and I do that by a linear structural equation model, just for simplicity. So here is a linear model on these random variables. I have here these variables is linear function of each other plus error term plus this exogenous term from the different subpopulations. Okay, we allow that A, this anchor, acts on Y and H. That's great. That's a relaxation of this very stringent condition. But of course, there's a price to be paid for this. There's now a fundamental identifiability problem. You cannot identify the causal parameter any longer. You cannot find this beta zero any longer. It's impossible. That's probably why people say this is forbidden and we give up on this. But we say, okay, we can do something which at least offers improvement. We call this causal regularization, and the aim is to find a parameter vector, a regression parameter vector, such that the residuals stabilize. So I look at my residuals, and I want to stabilize them, having the same distribution in some sense across my different environments, across my different perturbations. So I want to encourage orthogonality of residuals with A. So of course, every student would say, okay, we try this, right? We estimate the regression parameter by minimizing residual sum of squares, and we regularize or penalize such that the residuals are fairly orthogonal with this A variable, right? So psi is a regularization parameter. If you make psi large, the residuals are orthogonal to the A variable. That's this idea. It's not quite what we do. We look or define causal regularization as follows. We look at the projection, the linear projection on the column space of A. So A could be also multidimensional. And now we define our estimator as the following optimization. we minimize anti-projection residual length squared plus a regularization parameter projection residual length squared. Okay, just for illustration, for gamma equal 1, if I choose this regularization parameter as 1, this is least squares, right? You can always decompose least squares in anti-projection length squared plus projection length squared. For general values of gamma, we call this general causal regularization. Now you can do all sort of stuff with that. That's a very easy convex optimization problem. I can add, say, sparsity-inducing penalties. In addition, I can do additional loss of penalty, other regularization schemes. This is still a very easy convex optimization problem. Okay, it's easy to solve, but the question is, what does it solve, right? There's a fundamental identifiability problem. I cannot hope that it estimates this beta 0. It's impossible. And if you do this causal regularization, I will explain you now that it solves a worst case optimization problem over a certain model class of perturbations. And we call this model class shift perturbations. So let me introduce you to this model class. So we have a model for the heterogeneous data. This is corresponding to the scripty, the subpopulations I have observed in my data set. This is my linear structural equation model in this anchor regression. And there is an exogenous term here which comes from the different environments, the different subpopulations. Now I do a model for the future scenarios in script F, and these are just shifted versions of what I have in my data version. And what I model is I take the same linear regression matrix parameter here, the same distribution of the innovation error term, but I replace this exogenous contribution from the different environments just by any, not quite any, but by a shift vector V. This could be random or deterministic. And important here is that this V is in the same direction as the observed heterogeneity. This is kind of my extrapolation, right? I extrapolate in the same direction to what I've seen in the data across my heterogeneous subpopulations. So V is in the span of M, same direction, and it might be much, much larger than what I've seen in the data. It has a certain size gamma. And so here's the technical definition. V is in the C gamma. Essentially, the length L2 norm squared of V is gamma, and V is in the direction of the observed heterogeneity M times A. Now there is a fundamental duality theorem here. Let's look at the infinite sample version, where sample size would be infinity, to make this kind of very compact and easy to explain. Then this projection onto the column space of A becomes actually the conditional expectation. That is my PA. And the theorem is, for any beta, I can look at this worst case risk, worst case expected loss over all these shift perturbations in this C gamma space, same direction as the observed heterogeneity. This worst case risk is exactly equal to my causal regularization risk, namely anti-projection length squared, plus the same gamma. This is the gamma which measures the size of my perturbation, the same regularization gamma here of expected length of residual squared when projected to A. Of course, this is the infinite sample version of my objective function on the data. So worst case shift interventions do correspond in one-to-one relation with this causal regularization, and that means you just regularize. Instead of solving the left-hand side here, which is very hard, you just look at the right-hand side and regularize. To make the point clear for kind of application viewpoint, the left-hand side is the worst case test error in the future, right? What happens in the future under perturbations. The right-hand side is my criterion on the training population sample. This holds for any beta, hence it holds also for the argmin, right? And therefore, if you optimize here on the training population sample, you will have guarantees for predictive stability. This can be made rigorous also for finite samples. So robustness and this causal regularization, they really correspond to each other. And I just put up two pictures. Here is kind of adversarial robustness, is kind of a very hot topic in machine learning. I have a picture of Ian Goodfellow, and causality. I could put many pictures here. I have the one from Judea Pearl. Maybe I'll skip that slide. And the point is, indeed, one can improve prediction with this causal type regularization. There are quite interesting examples out there. There's interesting work by Leon Boutou in the causal robust machine learning community. So he was at Microsoft, he's now at Facebook, and he publishes quite promising results by doing similar things that what I just explained before. You want to regularize so that you are robust for future unknown scenarios. I'm more interested in the interpretation part. Science aims for causal understanding. This is a bit ambitious, right? Causal inference necessarily requires often untestable assumptions. And say in my anchor regression model I just explained, for example, we cannot identify this parameter beta theorem. Well, let's go back to this fundamental duality theorem. By this fundamental duality, I can look at a particular parameter, namely when I push the regularization parameter to infinity. So this is this B infinity, this is lim B gamma gamma to infinity, and B gamma is the solution of my regularized problem when I have a regularization parameter gamma. I can look at the residuals with y minus x B infinity. And it, by definition, leads to shift invariance of the residuals. I stabilize them. B infinity is generally not the causal parameter, but because of this shift invariance, I call it the diluted causal parameter. And so now we can talk about different notions of associations and what we're trying to do. So the most simple association between random variables is maybe marginal correlation. Then you can go, this is what we teach in statistics, you can go to maybe better association measures from regression, which is partial correlation. And then there's this very ambitious association of causality between random variables. And we're going somewhere in between with invariance. We want to have associations which are invariant, like this shift invariance, which I just defined before. Okay, so here's an interesting statement which I found by John Tukey, who's a very famous mathematician, also the co-inventor of FFT, and also a great statistician. So Tukey wrote about correlation and regression as follows. One of the major arguments for regression instead of correlation is potential stability. We are very sure that the correlation cannot remain the same over a wide range of situations, but it is possible that the regression coefficient might. We are seeking stability of our coefficients so that we can hope to give them theoretical significance. So Tukey argued we should go from marginal correlation to regression because of stability, also of course because of interpretation, but also because of stability. And we say, okay, we should go one step further and stabilize more. We should go to this maybe diluted causality where we have shift invariant residuals. And towards the end of my talk, I really want to show you maybe an application, how this works, how this can be used. So this is an exciting project together with Rudi Ebersold. He's a very famous biologist, a very renowned scientist for measuring proteins. And the goal here was to understand the cholesterol pathway a bit better. So the cholesterol pathway comprises maybe about 20 proteins. So Ebersold can measure the abundance of these proteins very well. And he also measured 3,934 other proteins which are outside the cholesterol pathway. And the ambitious question would be, what are the causal relations from these other proteins to these cholesterol proteins? That's a bit maybe too ambitious. And we ask, what is the diluted causal effect of these other proteins to the cholesterol proteins? So we have experiments with mice, two environments. One of them have a low fat, one of them have a high fat diet. It's a very high dimensional regression problem. My response variable y is the cholesterol pathway activity here. This is something like the first principal component of these 20 proteins, and the covariates x are all the 3,934 other protein abundances. Now you can run this causal regularization. You choose gamma very large. You get to this B infinity parameter. And I just show you a picture here. Now what you can do is you can measure importance, say, with respect to regression, but being non-invariant. This is kind of the regression importance on the x-axis. You can measure importance with respect to invariance, kind of this diluted causal parameter, how big it is. And then you see the importance of these different outside proteins on the cholesterol pathway. And what you see is that some of these proteins are very invariant, but they're not the most important in terms of regression. So we pushed this actually through very many other pathways, also looked at transcriptomics and so on and so forth. And the message is not all of the predictive variables from regression lead to invariance. So we stabilize regression. We go Tukey one step further, and we have different forms of validation. I'm not going into details. I also have a time constraint on my talk. But we do find that this invariance in that particular application, these protein abundances, it performs substantially better than regression association only. Let me just very quickly say that we can also address a bit, just a tiny little bit, this distributional replicability. So again, scholars have found that the results of many scientific studies are difficult or impossible to replicate. How can we do this? Well, this is maybe kind of almost obvious now, at least in this little framework with this anchor regression model. I can look at this diluted causal parameter, and here is a little theorem that this is actually replicable under certain conditions. The framework is, I look at this diluted causal parameter B infinity, which is estimated from, say, a first study, a first data set. Then I look at another data set, another study, and want to see whether I can replicate that parameter. So in this other data set, it's maybe a B prime infinity parameter. This is estimated from the second new data set. And now I assume, and of course this is a big assumption, that this new data set for replication arises from this shift perturbation model, which I introduced before. If this is true, if there's an additional small little assumption, then this parameter, this diluted causal parameter, is replicable, namely B infinity equals B prime infinity. As a last illustration, I want to show you how this works on this GTEC data, which I briefly introduced before. I remind you, we have 13 different tissues. We have gene expressions in every tissue of about almost 13,000 genes, sample sizes between 300 and 700. We have a target variable of interest. This is a target gene. We have expressions of all other genes. And now I have this anchor variable. And I have an additional 65-dimensional anchor variable. This encodes for potential confounders. This has been created by the consortium people, which comprises a lot of biologists. And the goal is estimation and finding on one tissue, and I want to see whether I can replicate on the other tissue. And here is the picture. So you can run now an algorithm on one tissue, say the lasso, L1 norm penalized linear regression. That's the green line. You take the top 10, say, variables. So on the x-axis, you see the top k features chosen. So if, for example, you take the top 10 variables from lasso, found on one tissue, and you want to see how much overlap is it with on the other tissue. How many of the selected feature from tissue 1 can be replicated on tissue 2? So if you run the lasso, you see here the amount of overlap. This is averaged over all the 13 choose 2 tissue pairs. And this is this diluted causality. This is the causal regularization solution, which brings much higher degree of replication. It's a different parameter though. This is for the diluted causal parameter, whereas say lasso is just for the least squares parameter. Let me conclude. We skipped a lot of the math. Many of our procedures have finite sample performance guarantees. I skipped that. One has to make the usual assumptions on sparsity, sub-Gaussian distributions with good concentration properties, well-behaved restricted eigenvalues on top of the concepts which I sketched today. Conclusions, as a final slide, interpretation and robustness are actually related to each other, at least in this framework of causality and distributional robustness I introduced today. Stabilizing and finding suitable invariances in large-scale data structures are highly useful in my view, and there's much open space for further development and on robustness and interpretability. Let me say that I still think that statistical thinking, where we think about sampling and other biases, quantifying and decision under uncertainty, stability and robustness is also one aspect of this, will remain to be very important. Thank you.
All right, thank you very much, Peter. I'll applaud on behalf of everyone present here. So if you have any questions, please submit them through the Q&A function at the bottom of your Zoom screen. There's one question already. I'll read it because I don't think everyone can see it. Could you explain again the meaning of the double-headed arrows, so the ones that point in both directions?
Yeah. Okay, I was maybe a bit quick, of course. Good question. So, for example, here, right? What's meant to be is, okay, these are multidimensional variables. So there's an x1, x2 to say an xp. And some of them point in this direction and some of them, some of the arrows go in that direction. So this is just a very shorthand notation. We could also think of through feedback loops. That's possible as well. Of course, this is a bit more a philosophical comment. There's probably always time involved in feedback loops, right? So we would need to have at least instantaneous time moments so that feedback could happen, but that's possible as well. So we can actually model this as a graph, where the graph is not directed acyclic. The graph could have loops. And then if you do that, just as a technical comment, you have to put an eigenvalue condition such that the system does not explode.
All right, thank you. So the next question is mediation analysis an educated proxy of causality?
Yeah, that's a great thing. This is, of course, I had no time, and I didn't mention anything on the huge, or not much about the huge literature on causality which exists. I should also maybe point out that one of the main successes of causality is randomized trials, right? So there we can have quite clean statements what the effect of an intervention is, how we can quantify this, how we can put confidence intervals around it. Now, mediation analysis is a very powerful tool to try to understand, say, in this little picture, which arrows go through another one and which are directly pointing to y. If you want to do this, you need much more know-how about the system. You need to know much more. This is a bit here. You need to know much more what the true system would look like. Maybe you would need to know the structure, the topology of the true system. And if you have that, then you could indeed start to quantify, well, how much of the effect of x2, well, this is not here in the graph, but how much would go through x1 and then on y. And I can look at some kind of mediator variables which kind of serve to answer this question. But it needs much more know-how. So I'm more in the framework. We don't know too much about the system, like in this proteomics example, there is not that much known. And we just rely more on this stability issue, trying to get some sort of more robust prediction. But it's a great thing to do, but it requires more input.
Right, thank you. So the next question, Peter, is can you give the audience some references to one or more key papers that cover the core of your talk?
Yeah, so you can go on my website, and so there is a paper which just appeared in Statistical Science. This is kind of a bit of a review paper. This is 2020. This is just written by myself. This covers quite a bit of this. And then we have an archive preprint out there on anchor regression. This is actually joined with Dominic. These are the first people here. This is joined with Dominic, Jonas, and Nikolai. So this is what I explained about this causal regularization. This paper will appear in the Journal of the Royal Statistical Society, Series B. That's also covering quite a bit of my presentation. The life science application with proteomics is mainly done with Niklas and Rudi Ebersold. We have a preprint out there, and we have a more biology. We have a preprint more on the methodology and the algorithms, and then one on the biology with a huge number of authors. That's also available on my website.
All right, thanks. And the next question is, does distributional robustness relate to actual statistical distributions?
Relate to statistical, let me just, is this, okay, here, can you,
yeah, maybe.
does distribution, okay, here I see it. Yes, it does. I mean, so the robustness per se not, but the robustness is formulated such that we look at these different statistical distributions in my framing under different scenarios, under different subpopulations. All of them have a distribution. I don't know what it is, but I want to be robust against these distributions. So this is kind of quite classical robustness, of course. So well, in my view, Huber's great invention on classical statistical robustness was to have kind of a target distribution like the Gaussian, and then you look what happens in the neighborhood of the Gaussian. So in some sense, this is the same story here, that we're looking also not necessarily in a neighborhood, but in a region around the target distribution, and the target distribution is what I have observed in the data, are my different distributions from a heterogeneous sample. And the difference of distributional robustness and classical robustness is, in classical robustness, you want to get rid of the outliers, you want to downweight the outliers. Here, you want to say, okay, they are there, I have to expect them in the future test data set, and the question is, how can I deal with them in doing good prediction? But yes, they do relate to statistical distributions.
Okay. One more question I have here in Q&A, two more. The first one, are you trying to distinguish causes and effects, or just is there just a dependence between them?
Yes, I do. I mean, ideally, I do. I try to know whether a certain, even in 2 dimensions, right, whether X causes Y or whether Y causes X. As I try to explain, this is extremely hard question if you just have data. And so if you could identify the causal effect, this would really mean I would know the directionality, that I could distinguish what is cause, what is effect. Now, of course, this is kind of almost a miracle if you could do that. And mathematically, we need to place assumptions in order that this is possible. And these assumptions are sometimes maybe very questionable, very stringent. And that's why we kind of try to relax a bit and say, well, this is maybe too hard. I rather go for this diluted causality where I cannot distinguish anymore what is cause and effect.
Okay. And here's a somewhat technical question. If you can, Please explain the construction of the matrix that is used for the projection operation.
Okay, that's the same matrix as if you do least squares. So you have a span, right, so you have a matrix. This is my A. I have the number of rows is my sample size, and I have a dimension, the number of columns. So I look at the span of the linear span of the columns, and I just project on the linear span of the columns. It's just the standard projection matrix onto the orthogonal projection matrix onto the linear span of the columns. And this is kind of like doing least squares on my linear span. It looks maybe kind of complicated in terms of formula, but it's actually a very simple thing to do.
Okay. And one final question is it provable that the set of causal structures is a subset of the set of invariant structures?
Yep, that is a very good point. Let me go to this picture. Of course, one can always find pathological cases, but that's this picture here. So under some sort of a faithfulness assumption, which means that there is not pathological cancelling of effects, which has maybe measure 0, right? Then this holds, and what we see is, so if there is a causal effect, then it is invariant. So we see this kind of clear relation here.
All right, thank you very much. And thanks everyone for attending and asking questions and for your engagement. I'd like to point out that there's one more talk coming up in the Matrix Online Seminar in December by Javier Torrebo from Google Cloud. So many of the people here may be interested in that talk. Peter, thanks again for getting up early in Switzerland, and I wish you a very good day. Really enjoyed your talk, and thanks everyone.